okay, summarize what we have done so far, right? Five formulas in this chapter. So first formula is current is the rate of flow of charge, I equal Q over T. Okay, so the 1 ampere is equivalent to 1 coulomb per second. All right, current is the rate of flow of charge or rate of flow of electric charge. Okay, then EMF is basically the voltage of the power source. All right, so it's the work done to drive 1 unit charge. Okay, work done by the source to drive 1 unit charge around the whole circuit. Okay, work done to drive 1 unit charge around the whole circuit. Right, then potential difference is the work done to drive 1 unit charge through the component only. All right, just the component. Okay, so work done to drive 1 unit charge through the component. Okay. Then resistance, we have learned it is the ratio of the potential difference to the current flowing across the component. All right. Okay. Then we learn also, that in series, the sum of the potential differences of the components is equal to the EMF of the battery. Okay. All right. The sum of the PDs. So in this case, V1, all right, and V2, okay, add together will be equal to V of the EMF. Right? Okay. The sum of the potential differences is equal to the EMF of the power source. Okay. This is for series circuit. All right. Only series circuit. Okay. Series circuit. Then for parallel circuit, then your V is constant. So if I were to put a voltmeter over here, okay, let me change the color. If I were to put a voltmeter over here, I call it V, and if I put a voltmeter over here, I call it V1, and a voltmeter over here, I call it V2, okay, they will all be the same. All right, V equal to V1 equal to V2. And as we have said before, okay, this is important for lighting circuits. Okay, lighting circuits always use, okay, always parallel. Always parallel. Okay, why? Right, number one, if one bulb blows, the others are not affected. Number two, all the bulbs would have the same PD across it. Okay? Okay, I'll repeat. Lighting circuits are always parallel because, firstly, when one lamp blows, the other lamps are not affected. Number two, all the lamps, each of the lamps, each branch will have the same PD. Okay? So here there are two bulbs in parallel. Okay? Each of the branches will have the same PD as the EMF. So if the EMF is 2 volts, then each of these lamps will be 2 volts. So no matter how many branches you add, right, the PD is constant. The PD will still be 2 volts. Okay? So that's for parallel. Any questions so far? Actually, this part is next chapter, DC circuits. But because it's related, so I just mentioned now. Okay, so next, when we come to the DC circuit, it'll be easier for us. Okay, I move on, Ken. Next, okay, we learn about that the longer the conductor, the higher the resistance, and the thicker the conductor, the lower the resistance. Okay, I repeat, if the conductor is short, all right, then the resistance is lower because it takes a shorter distance. There's a shorter distance for the charges to move through, so there's a lower resistance. Then when the conductor is long, okay, it will take a longer time for the charges to move through it, so there will be a higher resistance. All right. Then for thick and thin conductor, okay, thin conductor is harder for the charges to move through, okay, because it's very narrow, right? The charges will have to squeeze through that small cross-sectional area, okay? So there will be a higher resistance. Then when the conductor is thick, that means the cross-sectional area is large, okay? When the cross-sectional area is large, it's easier for the charges to go through, therefore the resistance is lower, okay? Right, so we have already done this, right? So which of the conductors have the lowest resistance? It will be the conductor that is the thickest and the shortest, right? So lowest resistance will be thick and short. Then highest resistance will be the thin and long one, right? Okay? So what we did was we combined the relationship, we expressed this relationship in the form of a mathematical expression. So we say that R is proportional to the length of the conductor, resistance is proportional to the length of the conductor, and resistance is inversely proportional to the cross-sectional area. Okay? So when we combine them together, right, we write it as resistance is proportional to length over area, okay? And since we know that when y is proportional to x, y is equal to a constant times x, right? So if r is proportional to L over A, okay, the length directly proportional to length, inversely proportional to cross-sectional area, therefore, you can put a constant there in front. R is equal to this constant times L over A. And this constant is named resistivity. Okay, resistivity. And it has a unit of ohm meter. Okay, this one I didn't mention last lesson, so I say it now. R is equal to rho L over A, right? So if you compare the units on both sides, right? Okay, if you compare the units on both sides, on the left-hand side is ohm for resistance, length is in meters, cross-sectional area is in meters square. Okay, so to balance the left-hand side and right-hand side, right? Okay, to balance left-hand side and right-hand side, this resistivity would have to be ohm meter. Okay, because ohm meter times meter is ohm meter square, then divide by meter square, the meter square will cancel off, you're left with ohm. You know what I'm saying? Right? This resistivity is ohm meter, right? Times meter is ohm meter square, then meter square and ohm meter square, right? The meter square cancel off, you're left with ohm. That's why the left-hand side will be equal to right-hand side. Okay? So that's why this resistivity has a unit of ohm meter. Okay, and if you look in your textbook, right, the lower the resistivity, the better the conductor, electrical conductor it is. Okay, so in the table in your textbook, silver has the lowest resistivity, right, on page 269, right? Okay, silver has the lowest resistivity, so it is the best conductor, right? Then next will be copper and so on, right? Then insulators will have high resistivity. Okay, so this resistivity is actually dependent on the material. Okay, material. So in O-level questions, when you say that, when the question says it is made from the same material, they are telling you rho is constant. Okay, if they tell you that, okay, conductor A and conductor B are made from the same material, or they say copper wire A, copper wire B, they are telling you copper because they are telling you that resistivity is the same. So this resistivity is about the material. Okay, material. All right, I move on. Okay, so I gave these two examples. Right, so first example, wire A 0.5 meters long has a resistance of 10 ohms. Wire B, same thickness, same material. Okay, when I say same material means the rho is constant, right? Same thickness means that cross-sectional area is the same. So we are only concerned with the length, and since resistance is proportional to the length, right? When from 0.5 meters to 4.0 meters, the length is 8 times. So since the length is 8 times, the resistance will be 8 times. Okay? So since the original resistance is 10 ohms, so 8 times of 10 ohms will be 80 ohms. Alright? Okay, then example 2. Okay, wire B has half the length and 4 times the cross-sectional area of wire A. Okay, what's the resistance of wire B if wire A has a resistance of 5 ohms? So this is the way that I suggest that you all express your working for questions that are a little bit more complicated. All right, the first question was very straightforward. Whatever you do to the length, you do to the resistance. Okay, the length times 8, the resistance times 8. So that one very direct. I didn't use this method. But for slightly more complicated questions, we will use this method. So we say that the original wire RA is equal to rho L over A, and then you know that it's 5 ohms, right? So it's 5 ohms. So rho L over A is 5 ohms. Okay? Then wire B has half the length and 4 times the cross-sectional area. So instead of writing L, we write half L, half the length. And instead of writing A, we write 4A. Okay? Then what we want to do is to take out the numbers. Take out the numbers, leaving only rho L over A here. Right? Okay, so we take out the number. So half divided by 4 is 1/8. So we take out 1/8. Right? We get 1/8 of rho L over A. And since rho L over A is 5 ohms, so you have 1/8 times 5. Okay, you get 0.625 ohms. Since it's exact, 3SF, we can leave it as it is. Okay, so this is where we stop. All right, now we go to the worksheet. Okay, for the first few questions, it's quite direct, so I'm not going to use the long method. Huh? So let's look at the question. Is it the correct version?
Yeah.
Okay. So first question, resistance 4 ohms. All right, for wire P. Then wire Q is 3 times the length. Okay. Same material, same thickness. So rho is the same, and cross-sectional area A is the same. Okay, so in which case, actually it's very straightforward. We have been saying resistance is proportional to the length. So if the new wire is 3 times the length, then the resistance will be 3 times, right? So we can just write RQ is equal to 3 times of the resistance of P. You get 12 ohms. Okay, so I didn't use a long method because it's quite straightforward. All right, so next one, length 2 meters, resistance 20 ohms. All right, then same thickness, the nichrome is the same. Nichrome means that the material is the same, right? So material is the same, so thickness is the same, so only the length changes. The length has been increased to 10 meters, that means 5 times, right? 2 meters to 10 meters is 5 times. So R is equal to 5 times of the original resistance. So we get 100 ohms. Okay. Do you pass this worksheet to Zelifa? Were you the one who took it?
She already has it.
Okay. Number 3, Resistance is 2.4 ohms, right? Okay, resistance is 2.4 ohms. Okay, the wire B has half the length, right? Same material, same thickness. Okay, so easy. R is equal to, so whatever you do to the length, you do to the resistance. So half the length, so half the resistance. That's 1.2 ohms. Okay. Number 4. Now it's about cross-sectional area. So, okay, let's read the question first. Cross-sectional area of 0.4 mm square. All right, resistance 10 ohms. Second wire, same material, same length, but now cross-sectional area is 1.6 mm square. Check that the unit is the same. Okay, make sure the unit is the same. As long as it's the same, you don't need to bother whether it's cm square or mm square. All right, it doesn't matter because what we are doing is comparing between the old wire and the new wire. So as long as the units are the same, you can compare. And you can see that from 0.4 to 1.6 is 4 times, right? Okay, 0.4 to 1.6 is 4 times. So let's use the longer method. Okay, the method that I recommended let's call it R1. Since they didn't give it a name, I just call it R1. So rho L over A is 10 ohms. R2, okay, the material is the same, length is the same. Okay, area is 4 times, so I write 4A. Okay, so I take out the 4 because it's denominator, so it's 1/4. All right, 1/4 rho L over A. So rho L over A is 10. Okay, from here, right? So 1/4 times 10 is 2.5 ohms. Okay? Now don't write 2.50, okay? There's no reason to use 3SF, right? You see 0.40 is 2SF. 1.6 is 2SF, right? So the final answer should be 2SF. Okay? All right, next. Okay, copper wire P has cross-sectional area of 0.5 mm square, resistance 0.5 ohms, Q same length. Okay, copper, both are copper, so same material, same length. Cross-sectional area is 0.25. In other words, it's halved, right? 0.5 to 0.25 is halved. So R equal to RP, they give it a name, so RP equal to rho L over A is 0.50 ohms. RQ, okay, is rho L over half A. Okay, the area is halved, everything else is the same. So half in the denominator, 1 over half is 2, right? Okay, so 2 times rho L over A. Okay, so it's 2 times of 0.5, so you get 1.0 ohms. Okay, 2SF, so 1.0.
Oh no, I switched the denominator.
Oh, okay.
Oh yeah. Oh wait, I timed wrong.
2 times half, alamak, I can get it wrong. Goodness. Must think so long. Huh? Okay. All right, number 6. Okay, we have wire X is 0.25 meters, cross-section area 0.5, and resistance 2.0. Wire Y, same material, length is 1.0. That means that the length is how many times? 0.25 to 1 is how many times? 4 times. That's recorded, by the way. Okay. Area 0.5 to 0.25 is how many times? 0.5 to 0.25. Halved, okay? It's halved, right? So your length was 4 times and your area is halved. Okay, so let's write down Rx, the O wire rho L over A is 2.0 ohms. The new wire, okay, rho L is 4 times. Okay, area is halved. All right, so 4 divided by half is 4 times 2, correct? Which is 8. So 8 rho L over A is 8 times 2 is 16 ohms. Agree?
I read wrong.
I will refrain from comment, otherwise it's recorded forever. Number 7. Okay, this one is a bit more tricky because radius is involved. Okay, so we are assuming, right? We are assuming that the cross-sectional area is circular. Okay, so we are going to assume that the cross-sectional area is circular, right, to be able to do this question, right? So radius is 0.25, okay? The new radius is, the second wire radius is 0.5, okay? That means the radius is 2 times, right? We need to know what's the relationship between radius and area, okay, in order to do this question. So we know that area of a circle is pi r square, okay? So that means that area is proportional to radius square lah. Okay, right? So if we square the radius, okay, we square the radius. So let's call it A1 and A2. So A2 equal to pi times 2 times of the radius squared, right? We get 4 pi r squared. In other words, is 4 times of area 1. Okay? That means it's 4 times of area 1. Right? So when the radius is doubled, the area will be 4 times. Okay? Because we square it. I say again, the radius is doubled, but the area will be 4 times. Because the relationship is square. Okay? If you halve the radius, then you will 1/4 the area. Understand? It's square. You have to square it. Alright? So once you know this relationship, the rest is easy. The length is from 1 meter increased to 4 meters, and then the area is 4 times. Right? So we continue with our normal working. R1 equal to rho L over A equal to 0.1 ohms. Okay, 0.1 ohm. Then R2 is rho. Okay, length is 4 times. Okay, for L. Area is 4 times. Because your radius is doubled, your radius is doubled, so your area is 4 times. So 4 times A. Right? 4 cancel off. Okay, so you're left with rho L over A again. So it's 0.1 ohm. Can? Any question? Any question? No. Oh, okay. Okay, we'll carry on. Alright, so for this table, right, you don't need to show the working in detail. Okay, so basically we know that whatever you do to the length, you just do to the resistance. Alright, it's directly proportional. Then area is inversely proportional. So whatever happens to the area, you just 1 over that. You divide by that. Okay? So let's look at it. The first original wire is 2 meters and 0.8 mm square. It has a resistance of 12 ohms. So new wire, okay, is 6 meters. That means it's 3 times, right? 3 times. So the resistance will be 3 times of 12 will be 36 ohms. Okay, the unit is in the heading, so I'm not going to write the unit here. All right? Okay? Unit is in the heading. Okay? Then next question. Length is 1, right, meter. So it's half of the original length. The cross-sectional area no change. Okay? So half of the original length. So half the resistance will be 6 ohms. Okay. Next one, length is the same. Cross-sectional area is how many times? 0.8 to 2.4 is how many times? 3 times, right? Okay. So when the area is 3 times, the resistance will be 1/3. Divide by 3, yeah? Okay, divide by 3. So 12 over 3 will be 4.0 ohms. Okay. Next, length is the same. Cross-sectional area is halved, right? So 1 over half is 2. Okay, 1 over half is 2 times. So 2 times of 12 is 24 ohms. Okay, are you all following? Okay, next. Length is halved, right? From 2 meters to 1 meter is half. Then from 0.8 to 1.6 is double, right? So you halve the length, that means you halve the resistance. Then you double the area, right? 1 over 2 is half, right? So it's half times half. Okay, do you all know what I'm doing? Length is doubled. Length is half. So you write half here. Then the cross-sectional area is doubled. So 1 over 2 is half. So half times 12 is equal to 3 ohms. Can? How many of you got 3 here? Okay, good. Right, next, length is 2 times. Okay. Then the cross-sectional area is halved, right? So that means 2 times for length. Cross-sectional area is half. That means 1 over half is 2. Okay, so 2 times 2 times 12 is 48 ohms. Agree? Okay. Then next one, the length is 1/4 from 2 to 0.5. Right, 2 to 0.5 is 1/4. Okay. All right. So 1/4 times, okay, area is halved. So 1 over half is 2. Okay, so quarter times 2 times 12 is 12 divided by 2, 6 ohms. Okay? Can? Any question?